We're about to look at something that should not exist. Not because it's forbidden by fantasy, but because, according to everything we thought we knew, the universe simply didn't have time to make it. We are staring at galaxies so massive, so organized, so early, that by the old rules they should still be cosmic debris. This is the youngest universe ever seen, yet it already looks mature, grown, heavy, bright. And if this is real, and it is then something about our most trusted cosmic story has been leaning on an assumption that may no longer hold, we're not tearing Einstein down. We're standing on his shoulders and realizing the view is stranger than expected. We start somewhere familiar, a night sky you've seen your whole life, pinprick stars, darkness between them. The quiet idea that the universe unfolds slowly, patiently, like a long novel written one page at a time. For over a century, Einstein's framework has told us how that story should flow. Space stretches, time dilates, gravity shapes everything. On the largest scales, his equations give us a universe that expands smoothly. Cooling as it goes, matter, clumping gradually under gravity's patient pull. That story worked. It worked so well that we stopped questioning its tempo. Then James Webb opened its eye. We didn't aim it at something exotic. No cosmic monsters, no speculative targets. We pointed it into what looked like empty sky patches already photographed by Hubble for decades. Darkness we thought we understood. Webb didn't just see deeper, it saw earlier, and what came back was not chaos. It was architecture. Galaxies with defined shapes, galaxies with dense cores, galaxies carrying the mass of the Milky Way or more, appearing when the universe was only a few 100 million years old. To put that in human terms, imagine walking into a city that should still be a construction site, and finding skyscrapers already lit, traffic flowing, history already layered into stone. According to the old expectations, this early universe should be clumsy, hot gas, small, irregular blobs, proto-galaxies still learning how to exist. Instead, Webb saw systems that looked settled. Stars had already formed, lived, and died enough times to enrich their surroundings with heavier elements. That takes time, not little time, cosmic time. But the clock says they didn't have it. We feel the tension immediately, even if we don't calculate it. The scale does the work for us. Gravity needs patience. Structure formation is slow because space itself is expanding, pulling matter apart as gravity tries to gather it. Einstein's equations don't forbid early galaxies, but they set a rhythm, a pace. And Webb is showing us a universe that may have been dancing faster than the music allowed. This is where attention tightens. Because nothing here is sloppy. The measurements aren't fringe. The telescope isn't guessing. Webb's infrared vision cuts through cosmic dust and redshift like a time machine with surgical precision. Light stretched by billions of years of expansion arrives exactly where Webb was built to see it. These are not optical illusions. They are signals that travelled nearly the entire age of the universe to reach us. And they're telling the same story again and again. Too big, too early, too organised. We are not saying Einstein was wrong. That would be too simple and too boring. His equations still describe gravity with unmatched accuracy. GPS satellites still need relativity to function. Black holes still obey his rules with terrifying loyalty. What's shaking is not the foundation, it's the extension. The cosmological interpretation layered on top of it. The assumptions about how matter behaved in the first few chapters after the Big Bang. Because to get galaxies like this, something must give. Either matter collapsed faster than expected, or gravity behaved slightly differently at early times, or there's more matter dark, invisible, influential than we thought, or the initial conditions of the universe were not as smooth and simple as our models preferred. Notice what's missing from that list collapse. This is not physics breaking, and this is physics pressing forward. We are standing at a frontier moment, the kind that only happens when observation outruns expectation. Einstein himself lived for these moments. He trusted equations. Yes, but he trusted reality more. When Mercury's orbit didn't behave, theory bent. When starlight curved around the sun, theory stood taller. Webb is that kind of test. Quiet, relentless, unignorable. And there's a human edge to this that we shouldn't miss. Every galaxy Webb sees is not just a structure, it's a lineage. Billions of stars, each potentially with planets, each planet with the raw materials for chemistry, complexity, maybe even life. The earlier these galaxies form, the earlier the universe becomes habitable in principle. That stretches not just cosmology, but our sense of cosmic timing. We may not be latecomers in a slow universe. We may be participants in one that rushed to complexity. That idea carries both privilege and vulnerability. Privilege, because a fast-forming universe is rich, early, fertile with possibility. Vulnerability, because speed often comes with instability. Rapid growth leaves traces, tensions, unresolved questions hiding under success. And now we're beginning to see them. The universe, it turns out, may have been more aggressive than Polite Equation suggested, more efficient, more eager to build. Gravity may have found shortcuts, dark matter may have clumped sooner. Small initial differences may have amplified faster than we allowed. This is not a crisis, this is a reveal. And we are only at the threshold, because the earliest galaxies are just the first crack in the facade. As Webb continues to look deeper, sharper, longer into star formation rates, into elemental abundances, into the faint glow between galaxies, the pressure will increase. Each new data point doesn't just add information, it asks a question. How fast can a universe grow up? And if it grew up faster than expected, what else did it do early, quietly, before anyone was watching? We are still inside Einstein's universe, but the lights just came on in rooms we didn't know were already finished. And whatever is waiting deeper inside will not be small. To feel how strange this really is, we have to rewind not gently, but violently back to the first moments where the universe had any right to organize itself at all. We're used to thinking of the Big Bang as an explosion. It wasn't. It was an expansion of everything, everywhere, all at once. No center, no edge, just space itself stretching, cooling, thinning. In the opening moments, the universe was so hot that atoms couldn't exist. Protons and electrons couldn't stay together. Light couldn't travel freely. Everything was a glowing fog of raw potential. Then, slowly, according to the story we told ourselves, things calmed down. Hydrogen formed, helium followed. Gravity began its long, patient work, tugging slightly denser regions into tighter knots. This is where Einstein's cosmological legacy quietly set expectations. His equations say gravity is powerful, yes, but it competes with expansion. Space is pulling matter apart even as gravity tries to pull it together. Early on, expansion dominates. Structure formation should be hesitant, tentative. The universe should stumble before it walks. But Webb is showing us a universe that may have sprinted. Those early galaxies aren't just big, they're bright. Brightness matters because it tells us stars are already burning intensely, and stars don't form instantly. Gas must cool, clouds must collapse, fragment, ignite. Massive stars must live fast and die violently, seeding space with heavier elements. Then a second generation forms, richer, more complex. This is chemical history, and Webb is seeing evidence that it's already well underway shockingly early. We're talking about galaxies existing 300, 400, 500 million years after the Big Bang, less than 4% of the universe's current age, in human terms. That's like finding a thriving global civilization a few months after Earth formed. Not just microbes, not huts, cities. So how did gravity move so fast? This is where the story tightens around Einstein, not to accuse him, but to interrogate the assumptions we built on top of his work. General relativity tells us how gravity behaves given a distribution of mass and energy, but cosmology adds ingredients: dark matter, dark energy, inflation, initial smoothness. These are not arbitrary, they're carefully chosen to match what we've observed so far. And now observation is pushing back. One possibility is that dark matter, the invisible scaffolding of the cosmos, clumped earlier and more efficiently than we expected. Dark matter doesn't emit light, it doesn't cool like gas, but it dominates gravity. If it formed dense halos faster, then normal matter would have fallen in eagerly, riding those gravitational wells like rails. Another possibility is that the early universe wasn't as uniform as we thought. Small ripples in density quantum fluctuations stretched across cosmic scales may have been more pronounced. Slight advantages amplified brutally. Regions that were just a little denser became much denser quickly. In a universe like that, winners emerge early. There's also a more provocative whisper: gravity itself may have behaved subtly differently at extreme early energies. Not a rebellion against Einstein, but a nuance. A regime where the familiar rules tilt just enough to accelerate structure formation. Even a tiny change, applied everywhere, could reshape the first billion years. None of these ideas are reckless. They're disciplined responses to data. And the data keeps coming. What makes this moment electric is that Webb didn't set out to challenge cosmology. It was built to look at exoplanet atmospheres, stellar nurseries, dusty galaxies. The cosmological shock is a byproduct, a side effect of seeing too clearly. When your vision sharpens, inconsistencies stop hiding. We feel this instinctively. When something forms too early, it threatens our sense of sequence, because before effect, preparation before outcome. But the universe doesn't owe us narrative comfort. It only owes us consistency, and even that can be more surprising than we expect. There's a human mirror here. We assume growth must be slow because our growth is slow. Civilizations take millennia. Knowledge accumulates painfully. But nature sometimes leaps. Phase transitions happen. Water freezes instantly at the right threshold. Stars ignite suddenly after long compression. The universe itself may have crossed critical thresholds faster than our linear intuition allows. And if that's true, then early galaxies aren't anomalies. They're signatures. Signatures of a universe that wasted no time becoming interesting. Now zoom in not with a telescope, but with perspective. Each of those early galaxies likely hosted billions of stars. Around many of those stars, planets may have formed: rocky ones, water-rich ones, carbon-bearing ones. The raw ingredients of complexity were in place far earlier than we ever imagined. We are not saying life existed then, but we're saying the universe became capable of life startlingly fast. That reframes humanity's position, not as late bloomers in a long empty cosmos, but as part of a universe that rushed towards structure, chemistry, and possibility. That's both humbling and unsettling, because speed leaves less margin for error. Fast formation can amplify violence. Early galaxies were turbulent supernovae roaring, black holes feeding aggressively, radiation flooding space. It was a harsh nursery, yet out of that chaos came order. And that brings us back to Einstein, not the monument, but the man. He never believed theories were sacred. He believed they were provisional maps. As far as the laws of mathematics refer to reality, he warned, they are not certain. He expected refinement, correction, surprise. James Webb is not tearing up the map, it's adding terrain. The universe didn't break the rules, it played them with more intensity than we anticipated. And now, as we push deeper, measuring star formation rates, mapping dark matter halos, tracking the faint background glow of the first stars, we're approaching a question that's bigger than any equation. Was the early universe optimized for speed? And if it was, what does that say about the kind of universe that eventually made us? We are still moving forward, and the scale is about to get even larger. To understand just how deep this goes, we have to widen the lens until individual galaxies stop feeling like objects and start feeling like consequences. Because galaxies don't form in isolation, they emerge from a cosmic environment, a pressure cooker defined by expansion, energy, and an invisible architecture we barely perceive. When Webb shows us mature galaxies appearing absurdly early, it's not just telling us something about stars, It's telling us something about the entire universe at that moment, its density, its temperature, its hidden forces. Picture the universe at 400 million years old. Space is smaller, everything is closer together, radiation is still intense. The cosmic background glow is brighter, hotter, more aggressive. In theory, this environment should resist order. Energy smooths things out. Expansion stretches everything thinner, and yet structure not only survives, it flourishes. This is where the idea of dark matter stops being abstract and starts feeling like destiny. Dark matter outweighs normal matter by roughly 5 to 1. You can't see it, you can't touch it. It passes through everything except gravity, but gravity is enough. In the early universe, while normal matter was still fighting radiation pressure, dark matter was already collapsing silently, forming dense knots, gravitational traps waiting to be filled. If those traps formed earlier or denser than expected, then galaxies didn't have to struggle into existence. They fell into place. We don't see dark matter directly. We see its fingerprints in how galaxies rotate, in how clusters bend light, in how large-scale structure forms a cosmic web of filaments and voids. Webb's discoveries suggest that this web may have snapped into place far faster than our simulations predicted. And simulations matter here. For decades, cosmologists have run universe-sized experiments inside supercomputers. They feed in Einstein's equations, dark matter properties, initial conditions measured from the cosmic microwave background. They let gravity run, and they watch galaxies slowly emerge over billions of years. Those simulations now have a problem. They don't produce enough big galaxies early enough. Not even close. This isn't a small discrepancy. It's not a rounding error. It's a tempo mismatch. The simulated universe is cautious. The real universe was bold. So we ask, what ingredient did we underestimate? One answer might be feedback. The violent processes inside early galaxies, supernova explosions, radiation from young stars, jets from feeding black holes were thought to slow growth by blasting gas away. But what if, in the early universe, feedback accelerated formation instead, compressing gas, triggering new bursts of star formation, building mass in runaway cycles? Another answer points to black holes. Webb has also glimpsed something else that shouldn't be so common, so early actively feeding supermassive black holes, not stellar mass remnants. Monsters with millions or billions of times the Sun's mass, already entrenched at galactic centers. Black holes that big require either impossible growth rates or impossible beginnings. If black holes formed from the direct collapse of enormous gas clouds skipping the slow stellar phase entirely, they could seed galaxies fast. Their gravity would deepen central wells, pulling in matter, stabilizing structure, accelerating assembly. This is still frontier science, but the direction is clear. The early universe may have had shortcuts, mechanisms that bypassed the slow ladder we assumed everything had to climb. And here's where Einstein's shadow looms large again. General relativity doesn't tell us how matter arranges itself. It tells us how space-time responds once it does. Cosmology fills in the story of arrangement. If that story needs revision, relativity remains untouched, but our narrative of cosmic adolescence changes dramatically. Instead of a slow, awkward youth, the universe may have experienced a rapid growth spurt. This reframes something profound. Cosmic maturity may not be rare. It may be the default outcome of a universe tuned just right. Now bring humanity back into the frame. Every time we discover something formed earlier than expected, we're forced to confront a quiet bias that complexity is fragile, that it requires long preparation, that it's unlikely. Webb is whispering the opposite. Given the right conditions, complexity rushes in. Stars ignite quickly, galaxies assemble decisively, black holes anchor structure early, chemistry spreads fast. We exist not at the end of a slow miracle, but in the aftermath of a rapid one. That doesn't diminish us, it contextualizes us. Because speed doesn't guarantee stability. Early galaxies were violent places, star formation rates were extreme, radiation fields were lethal, black holes were ravenous. Any early life, if it existed, would have faced relentless hostility. Survival still mattered. Adaptation still mattered. But the stage was built early, and that means the universe has been old enough for stories like ours far longer than we assumed. As Webb keeps staring deeper, it's beginning to trace the transition point, the moment when the universe flipped from smooth to structured, from simple to layered. That transition is where Einstein's elegant equations meet messy reality, where averages give way to outliers, where small differences explode into galaxies. We're not at the peak yet, because the next question isn't about galaxies. It's about time itself. If structure formed this fast, then the early universe didn't just evolve, it accelerated. And acceleration in cosmology is never innocent. Something was pushing. Something was shaping. And we are getting closer to the moment when that push reveals its true nature. Acceleration changes everything. We usually associate it with the modern universe, dark energy stretching space faster and faster, galaxies fleeing each other toward an unreachable horizon. That story is familiar, comfortable, but what Webb is hinting at lies much deeper, much earlier. A suggestion that acceleration wasn't just a late-stage phenomenon. It may have left fingerprints right at the beginning. To feel this, imagine time compressed. In the early universe, every million years mattered more than a billion does now. Density was higher, energy was thicker, small causes had outsized effects. A slight advantage didn't just grow, it detonated into dominance. This is a regime where intuition fails, where slow and steady loses authority. Einstein gave us space-time as a dynamic thing capable of stretching, bending, responding. But he couldn't tell us why it began in one state rather than another. Cosmology filled that gap with inflation, a brief, violent burst of expansion that smoothed the universe, flattened it, and seeded the tiny fluctuations that would later grow into everything. Those fluctuations were supposed to be gentle, measured, uniform. Webb is forcing us to ask whether some of them were anything but. If the primordial universe contained regions just slightly more primed, slightly more eager to collapse, then those regions could have sprinted ahead, forming stars and galaxies while the rest of the cosmos was still waking up. Not a violation of physics, an exploitation of it. This reframes the earliest light. The first stars, population 3 stars, were thought to be massive, short-lived, and isolated, bright but rare. They were the universe's first experiments with nuclear fire, but Webb's observations suggest their descendants may have multiplied faster, clustered earlier, and organized sooner than we imagined. Their death seeded space with carbon, oxygen, iron, the scaffolding of complexity almost immediately. The universe didn't linger in innocence. It moved fast into consequence, and consequence leaves records. Webb isn't just seeing galaxies, it's measuring spectrochemical fingerprints encoded in light. These tell us how enriched a galaxy is, how many generations of stars lived and died inside it. Some of these early galaxies look chemically experienced. That's the unsettling part. Experience implies history. History implies time. And time is what they weren't supposed to have. So we start stacking possibilities. Maybe inflation left more variation than we assumed. Maybe dark matter interacts in subtle ways we haven't modelled. Maybe early star formation was brutally efficient. Maybe black holes were born large, not grown patiently. Each option preserves Einstein, none preserve complacency. And there's a deeper undercurrent here, one that touches philosophy as much as physics. We tend to think the universe becomes interesting gradually, that meaning accumulates slowly, that complexity is a rare achievement at the end of a long road. But the data is nudging us toward a more unsettling vision, that complexity may be an attractor, that under the right conditions, matter doesn't resist organization, it seeks it. This doesn't make the universe friendly, it makes it intense. Because attractors come with violence. Matter rushes inward. Energy releases explosively. Black holes grow by destruction. Stars live fast and die young. Order is forged through catastrophe. We are products of that process. Zoom out further. If galaxies formed early and fast, Then the cosmic web, the vast structure of filaments and voids spanning billions of light years, also began assembling sooner. That web governs everything that follows, where galaxies cluster, where gas flows, where future stars ignite. Early changes ripple forward across all of time. This means the early universe wasn't just fast, it was decisive. And decisiveness is terrifying in a system this large. Because once a structure locks in, it shapes billions of years of outcome. Tiny early differences become eternal facts. Entire regions of the universe may have been advantaged or starved from the very beginning, not by chance, but by speed. There's a human echo here that's hard to ignore. We know how early conditions shape lives, childhood environments, initial resources. Small head starts that compound relentlessly. The universe may work the same way, not fair, not slow, just consequential. Einstein understood this intuitively. He distrusted randomness without structure. He believed the universe had an underlying order, even if we could only glimpse it indirectly. Webb is not contradicting that belief. It's intensifying it. Because a universe that organizes early is a universe with strong internal logic. We are now brushing against a possibility that makes scientists careful and storytellers lean forward. The early universe may have been more efficient than we imagined. Not wasteful, not hesitant. Efficient at turning energy into structure, chaos into hierarchy. If that's true, then our current models didn't fail because they were wrong, but because they were conservative. They assumed the universe would take its time. It didn't. And as Webb keeps looking toward the faintest galaxies, the dimmest glow, the edge where the first light ever emerged, we are approaching the moment where efficiency becomes inevitability. Where early acceleration stops being a detail and starts looking like a defining trait. The question now isn't whether Einstein's cosmology needs refinement. The question is whether the universe has been telling us from the very beginning that it prefers speed over patience. And if it does, what does that say about everything that comes next? If the universe prefers speed, then the first billion years weren't a warm-up. They were a sprint. And sprints leave scars. Because when structure forms this fast, it doesn't do so gently. It rips energy out of smoothness and concentrates it violently. Gas collapses. Radiation spikes. Gravity doesn't negotiate, it commits. The early universe, seen through Webb's eye, begins to look less like a calm expansion and more like a controlled avalanche. This forces us to refeel something we thought we already understood. The Big Bang wasn't just the beginning of space. It was the beginning of competition. Regions of the universe didn't grow equally. Some won early, some fell behind. And once gravity tips the balance, recovery is impossible. Matter flows downhill forever. In our older cosmological picture, this competition was slow, fair, in a cosmic sense. But Webb's galaxy suggests something harsher, a universe where advantage compounds brutally fast, where the first dense regions didn't just get ahead, they locked in dominance. That's not a small shift in story, that's a change in personality. Now let's bring Einstein directly into the frame again, not as a symbol, but as a constraint. General relativity allows space to curve, stretch, and evolve, but it doesn't decide initial conditions. It doesn't tell us how lumpy the universe should start. Those details come from inflation, from quantum fluctuations magnified to cosmic scales. For decades, the story was that inflation smoothed almost everything out, leaving only tiny, well-behaved ripples. But what if inflation left behind a little more texture than we assumed? Not chaos, just enough unevenness to let gravity bite early and hard. Even a slightly rougher beginning would be invisible in the cosmic microwave background we measure today, smoothed by time, blurred by distance. But its consequences would echo forward as exactly what Webb is seeing galaxies that look like they skipped adolescence. And here's the uncomfortable realization. If that's true, then the universe didn't just allow early complexity, it encouraged it. Which brings us to a dangerous thought, dangerous because it feels like purpose. Even though it isn't. The universe doesn't plan, but it does respond, and when the laws allow rapid structure, Structure happens everywhere it can. We see this pattern at every scale. Clouds collapse into stars faster than expected. Stars gather into clusters. Clusters merge into galaxies. Galaxies fall into filaments. Acceleration cascades. The early universe may have been primed for cascade after cascade after cascade. Now, let's talk about one of the most unsettling signals Webb has hinted at, something that sits right at the edge of what we can currently confirm: stellar mass. Some of these early galaxies appear to contain too many stars for their age. Not just bright stars. Total stellar mass that implies enormous amounts of gas had already cooled, collapsed, and converted into stars with astonishing efficiency. Gas cooling is not trivial. It requires radiation to escape. It requires metals to help shed energy. It requires time. Unless the early universe had help. That help could have come from molecular hydrogen cooling more effectively than expected, or from shock compression during rapid mergers, or from radiation fields that paradoxically triggered collapse instead of suppressing it. Again, none of this breaks physics. It exploits corners of it. And as each corner lights up, the comfortable middle dims. There is also a psychological trap we're stepping into, one we need to be aware of. We keep saying too early. Too early relative to what? Relative to us. Relative to models calibrated on a quieter, older universe. Relative to expectations shaped by what we already knew how to simulate. Webb isn't showing us a universe that's impossible. It's showing us a universe that's less patient than we assumed. And patience is a human projection. The cosmos doesn't wait for elegance. It obeys constraints and follows gradients. Where energy can fall, it falls. Where structure can grow, it grows. If the early universe was dense enough, cold enough, and uneven enough even briefly, then rapid complexity isn't miraculous. It's inevitable. Now pause and feel the scale again. We're talking about events that happened more than 13 billion years ago, before Earth existed, before the Sun ignited, before our galaxy finished forming its disk. And yet those moments are shaping the universe we inhabit now. The large-scale structure around us, the distribution of galaxies across hundreds of millions of light-years may carry the imprint of that early sprint, which means we are living inside the outcome of a decision made by physics before time had depth. That's not mystical. It's sobering, because it reminds us that the universe doesn't revise its early drafts. It commits. Einstein once described relativity as revealing a block universe, where past, present, and future coexist in a four-dimensional structure. Webb is making that idea visceral. We are seeing the past not as memory, but as architecture still holding, still constraining, still shaping what's possible now. And here's the human edge again. If the universe builds fast and commits early, then our existence is not the result of endless fine-tuning over eons. It's the result of a universe that was structurally capable of complexity almost immediately, and then never lost that capacity. We are not late beneficiaries. We are inheritors. But inheritances come with debts. Because a universe that accelerates early also burns energy fast. It produces extremes quickly. It creates black holes early. It seeds violence early. The same efficiency that builds galaxies can sterilize environments, flood space with radiation, and collapse matter beyond retrieval. The early universe was generous but ruthless. And that brings us closer to the brink. Because if speed is fundamental, then the greatest structures in the universe may have formed faster than even Webb has shown us so far. And the next thing we have to confront is not a galaxy. It's a monster hiding in plain sight, one that challenges not just cosmology's timeline, but its sense of scale. The monster doesn't announce itself. It doesn't glow like a galaxy or shimmer like a nebula. It announces itself through absence, through missing light, through motion that shouldn't make sense, through gravity that feels overqualified for the job it's doing. Supermassive black holes. Webb didn't go looking for them this early. No one expected them to be common. According to the older story, black holes had to grow up the hard way, born from dying stars, then fatten slowly over hundreds of millions of years by swallowing gas and merging with others. Growth by patience. Growth by attrition. But patience is exactly what the early universe seems to lack. Webb, along with other observatories, is finding quasars blazing beacons powered by feeding black holes existing when the universe was less than 1 billion years old. Some of these black holes already weigh 1 billion times the mass of the Sun. That's not impressive in isolation, it's terrifying in context. Because to reach that mass so early, a black hole would have to grow at near maximum efficiency continuously, without interruption, from almost the moment the first stars existed. That's like a human infant becoming the size of a city before finishing elementary school without ever stopping to eat, sleep, or breathe. Something doesn't add up. And when something doesn't add up in cosmology, it usually means we've misunderstood the starting point. One possibility is radical and increasingly unavoidable. What if some black holes weren't born small? What if the early universe produced direct collapse black holes objects formed when enormous clouds of gas collapsed straight into a black hole without fragmenting into stars first? No slow ladder, no stellar childhood, just immediate gravity overwhelming everything else. If conditions were right, if gas was dense, hot enough to avoid fragmenting and shielded from disruptive radiation, then entire regions could have imploded directly into black holes tens of thousands, even millions of solar masses at birth. From there, growth becomes easy. These black holes would anchor galaxies like keystones. Their gravity would stabilize disks, funnel gas inward, ignite star formation around them, and lock in early structure. Galaxies wouldn't struggle to assemble. They'd snap into place around a central void. This flips the narrative. Instead of galaxies birthing black holes may have birthed galaxies. Einstein's equations allow this. They don't forbid it. Space-time doesn't care whether mass arrives gradually or all at once. But our cosmological expectations did. We assumed the universe preferred incrementalism. Webb is asking us to confront a universe that prefers decisive collapse. And once you allow that idea, everything accelerates. Early black holes deepen gravitational wells. Deeper wells pull in more matter faster. More matter feeds faster star formation. More stars mean more metals. More metals mean more cooling. More cooling means faster collapse. Feedback becomes a flywheel. The early universe may have been a machine for turning density into hierarchy. Now step back and feel the implication. If supermassive black holes formed early and widely, then the universe's violent heart was beating almost immediately. Energy was being released on colossal scales, jets blasting across intergalactic space. Radiation carving paths through gas. Matter being rearranged violently and irreversibly. This wasn't a quiet childhood. It was a forge, and humanity billions of years later is living inside the products of that forge. There's something unsettlingly intimate about this. The iron in your blood, the carbon in your cells, the oxygen you breathe all were processed in environments shaped, directly or indirectly, by these early titans. The universe didn't just make stars early, it made engines early. Engines that rewrote their surroundings. And here's the deeper tension. If black holes formed this early, then our models of early cosmic radiation, reionization, and structure formation all shift. Black holes don't just sit there, they act. They ionize gas, they heat space, they regulate which regions can form stars and which are sterilized. This means the early universe may have been far more uneven than we imagined, not just in density, but in habitability. Some regions may have blossomed, others may have been scorched. Speed again, efficiency again. And here we brush against something that makes scientists uncomfortable, and storytellers lean in the idea that the universe may naturally produce extremes first and moderation later. The biggest stars, the biggest black holes, the most violent events, all early. Balance comes later, after energy is spent and gradients soften. We live in a calmer universe, not because it was always calm, but because it burned through its fury long before we arrived. Einstein once worried that singularity's points of infinite density signaled the breakdown of his theory. He hoped nature would avoid them. The universe didn't listen. Black holes are real. Singularities are hidden, but their consequences are everywhere. Webb is now suggesting that singularity-adjacent behavior wasn't rare in the beginning. It was foundational. And this brings us to a chilling thought. If the early universe produced black holes efficiently, then some of the structure we see today may be tracing paths laid down by objects we can no longer see. Black holes that merged, black holes that went dormant, black holes that shaped regions and then vanished into darkness. Ghost architects. We are not just seeing early galaxies. We are seeing the aftermath of invisible decisions made by gravity at its most extreme. And we are still not at the peak. Because black holes aren't the only invisible players. There is something even larger, more pervasive guiding this early acceleration. Something that doesn't collapse into points, but stretches across everything. Something we name only because we don't understand it yet. Dark energy has a past. And Webb is pushing us closer to it. Dark energy usually enters the story at the end. A quiet villain, a late twist, the force that takes over once galaxies are already built, once stars are aging, once the universe has had its chance to settle. It's the reason expansion accelerates now, the reason distant galaxies are slipping away faster and faster, the reason the future looks empty. But Webb is forcing us to ask an uncomfortable question. What if dark energy wasn't always quiet? What if it had an early role, subtle, indirect, but decisive? We don't feel dark energy locally. It doesn't bind atoms or shape planets. Gravity dominates where matter is dense. But in the early universe, everything was dense and yet expansion still mattered. The balance between attraction and repulsion was razor thin. A tiny shift in that balance, early on, could cascade forward into everything we see. Standard cosmology treats dark energy as simple, constant, featureless. A background pressure that only becomes important once the universe thins out. But that assumption exists because it worked, because it matched what we could observe. Webb is showing us the cost of that convenience. If early galaxies formed faster than expected, one possibility is not that gravity was stronger, but that expansion briefly behaved differently. That the early universe had phases where space didn't stretch quite as smoothly, or where the energy driving expansion wasn't constant, but evolving. Not chaotic, just dynamic. This isn't fantasy. In fact, it echoes ideas long kept at the edges of mainstream cosmology, ideas about early dark energy, transient fields, or scalar components that briefly influenced expansion before fading into the background. If such a component existed, it could do something counterintuitive. It could help structure form. By changing the rate of expansion just enough, slowing it here, speeding it there, it could give gravity windows of opportunity, moments where matter had time to collapse before space pulled it apart again, short epochs where the universe leaned towards structure instead of smoothness. Webb doesn't prove this, but it makes it plausible. And plausibility is dangerous. Because once you admit the universe's expansion history might be more textured than a single smooth curve, everything becomes negotiable again. The timing of reionization, the growth of black holes, the distribution of galaxies, even the interpretation of the cosmic microwave background the oldest light we see may need rereading. Not rewriting. Re-listening. There's a human instinct to want a clean origin story, one inflation, one expansion rate, one smooth unfolding. But nature rarely rewards simplicity with obedience. It rewards it with usefulness until higher resolution arrives. Webb is higher resolution. And with higher resolution comes friction. Now feel the emotional weight of this shift. For decades, Einstein's cosmological framework gave us a universe that felt restrained, elegant, predictable at scale. Change happened slowly. Extremes were rare. The cosmos felt like a vast, stable stage. What Webb is revealing is a universe that was more alive, more reactive, more willing to seize brief conditions and turn them into permanent outcomes. That doesn't make it chaotic. It makes it opportunistic. And opportunistic systems don't wait. They exploit gradients, they amplify noise, they convert possibility into fact before equilibrium can erase it. Life does this. So does the early universe. This is where the narrative turns inward. Because we are made of the same logic. Our brains latch onto early advantages. Our histories compound. Small accidents early in life shape entire trajectories. We know this pattern intimately. Seeing it written across the universe doesn't comfort us. It confronts us. The cosmos may not be fair. It may not be gradual. But it is consistent. Consistency doesn't mean gentleness. It means consequences. Now bring Webb back into focus. Every new observation it makes, every deeper exposure adds pressure to this emerging picture. The telescope isn't shouting, it's accumulating. A galaxy here, a black hole there, a spectrum that's just a little too mature, a mass estimate that's just a little too high. No single result overturns cosmology. Together they bend it. And bending is where Einstein's legacy is strongest. Relativity itself was born from bending of light, of time, of intuition. Einstein taught us that the universe doesn't snap to our expectations, it curves around them. We are watching that happen again, not with chalk and equations this time, but with photons that left their sources before Earth existed. There is a quiet audacity in that. Light from the early universe travelled for over 13 billion years, survived every expansion, every perturbation, every cosmic accident, and arrived just in time to tell us our story was incomplete. That's not coincidence. That's perspective. We're still inside Einstein's universe, but we're no longer standing where we thought we were. We're closer to the beginning, closer to the moment where expansion, gravity, and energy negotiated the terms of everything that followed. And the negotiation may have been faster, sharper, and more decisive than we allowed. The next thing we have to confront is not energy, not matter, not even time. It's expectation. Because the greatest shock Webb delivers is not that the universe behaved differently. It's that it behaved better at becoming complex than we ever imagined. And once you accept that, the future stops looking empty. It starts looking inevitable. Inevitability is a dangerous word. We usually reserve it for endings for heat death, for darkness, for the slow thinning of everything until nothing can touch anything else. But Webb is quietly suggesting that inevitability may belong to the beginning instead. That complexity wasn't a lucky accident. It was a phase change. And phase changes don't ask permission. When water freezes, it doesn't debate molecules. When iron magnetizes, it doesn't negotiate domains. When conditions cross a threshold, behavior reorganizes instantly. The early universe may have crossed several thresholds in rapid succession density, temperature, expansion rate, and each crossing unlocked a new mode of structure. Stars weren't optional, galaxies weren't improbable, black holes weren't late. They were consequences. This reframes the shock entirely. We've been treating Webb's discoveries as anomalies, exceptions that strain the rulebook. But what if the rulebook was always missing a chapter? What if the early universe didn't struggle toward complexity, but fell into it? That idea carries weight, because it means Einstein's cosmological picture space expanding, matter responding. Gravity sculpting was never meant to predict hesitation, it was meant to predict response, and the early universe responded with urgency. Now zoom into one of Webb's most unsettling contributions, scale consistency. It's not just that we see one or two early massive galaxies. We see many, across different regions, at different redshifts. The pattern repeats. This isn't a fluke, it's a population. Populations don't lie, they announce regimes. When you see the same outcome emerging independently across vast distances, it means the underlying conditions were global. The universe, everywhere, was primed. That's the moment where coincidence dies. And this is where expectation finally breaks. Because the standard cosmological model, the one built on Einstein's equations plus dark matter, dark energy, and inflation was calibrated to a universe that eased into structure. It predicted a long cosmic dawn, with faint, scattered lights slowly multiplying. Webb is revealing something closer to a cosmic ignition, a dawn that flared. This doesn't erase the old picture, it sharpens it. The early universe still expanded, Inflation still smoothed large scales, dark matter still guided structure, but the transitions between phases, between smoothness and clumping, between gas and stars, between stars and galaxies may have been far more abrupt. Abrupt transitions are efficient. Efficient systems don't waste time. Now consider the implication for something even larger than galaxies' cosmic time itself. We measure cosmic age by expansion, by how stretched the universe is compared to its beginning. But age is not experience. A short, dense, violent era can do more work than a long, quiet one. The first billion years may have packed more structural change than the next 10 combined. If that's true, then the universe aged unevenly. Not in years, but in consequence. The early universe grew old fast. And that casts a new light on Einstein's most counterintuitive gift: time is not absolute. It flows differently depending on motion and gravity. Near massive objects, time slows. In dense regions, clocks tick differently. The early universe was the densest region of all. Time, in a sense, was heavy. This isn't poetic license, it's physics refracted through scale. Processes ran hot, fast, intense. What looks like too much happening too early may simply be what happens when the universe is compressed into its most efficient configuration. We are judging a sprint by marathon rules. And now that misjudgment is catching up to us. There's another layer Webb is exposing, one that doesn't show up in mass or brightness, but in uniformity, despite the violence, despite the speed. The early universe still obeyed large-scale order. Galaxies align along filaments, voids open between them. Structure has coherence. This tells us something profound. Speed did not destroy order, it amplified it. That's not what we expected. We assumed violence would randomize outcomes. Instead, it seems to have selected them. The cosmic web didn't fray under pressure, it tightened. The universe didn't fragment into chaos, it organized into hierarchy. That hierarchy persists today. We live in a universe with preferred scales: planets, stars, galaxies, clusters. These aren't arbitrary. They're stable solutions. The early universe may have found those solutions quickly and then locked them in. Once locked, change becomes cosmetic. And this is where the emotional center shifts. Because if complexity was inevitable early, then the universe didn't wait billions of years to become interesting. It became interesting as soon as it was allowed to. Which means our story isn't about emergence from emptiness. It's about inheritance from intensity. We are not living at the end of a long experiment. We are living inside the stabilized aftermath of an early explosion of structure. That changes how we think about rarity. Life may still be rare, intelligence may still be fragile, but the conditions that make them possible may not be. Those conditions: chemistry, energy gradients. Stable stars arrived early and widely. The universe didn't need to warm up. It was ready. Now let that settle. For generations, Einstein's cosmology made us feel small by stretching time and space beyond comprehension. Webb is making us feel small in a different way by showing how quickly the universe achieved what we thought required patience. We are not late. We are not early. We are on time relative to a universe that moved fast, built fast, and then slowed into refinement. And refinement is where stories like ours can exist. The next thing Webb is forcing us to confront is subtle but destabilizing. If the early universe was this efficient at building structure, then our predictions about the future may be equally incomplete. Because a universe that surprises us at the beginning may not behave the way we expect at the end. And that brings us to the horizon, not the edge of space, but the edge of confidence. Where even Einstein would pause. Confidence is a fragile thing in cosmology. It's built not from certainty, but from repetition, from models that work again and again until we stop flinching when we extrapolate them forward. Einstein's equations earned that trust. They worked for Mercury, they worked for starlight, they worked for black holes, and when we scaled them up layered with dark matter and dark energy, they seemed to work for the universe itself. Until the universe started answering questions we didn't think to ask. Webb's early galaxies don't just challenge timing, they challenge extrapolation. The assumption that because the universe behaves one way now, it must have behaved proportionally the same way then, and will behave proportionally the same way later. That assumption is comfort masquerading as rigor. The early universe is reminding us that regimes matter. Physics doesn't change its laws lightly, but it changes its dominant effects all the time. Pressure dominates here, gravity dominates there, expansion dominates later. What Webb is hinting is that we may have misjudged which effects dominated when it mattered most. And if that's true for the beginning, it may be true for the ending. We talk about the fate of the universe with remarkable confidence. Eternal expansion, galaxies drifting apart, stars burning out, black holes evaporating, a slow fade into irrelevance. It's elegant, it's tidy, it's emotionally neat. But elegance didn't rule the early universe. Efficiency did. The same universe that rushed into structure might not drift gently into emptiness. This is not speculation, it's symmetry. If cosmic history has already surprised us once, at the very first chapter, then assuming the final chapter will behave politely is an act of faith, not physics. Now pause and bring Einstein back this time in his most uncomfortable role. Einstein introduced the cosmological constant to keep the universe static. When expansion was discovered, he reportedly called it his greatest blunder. Later, that same term returned as dark energy rescuing cosmology again. Accelerating expansion, matching observation. That's not failure. That's humility enforced by reality. Einstein's universe bent not because he was wrong, but because the universe refused to stay simple. Webb is continuing that tradition by showing us early acceleration not of space necessarily, but of structure. It's forcing cosmology to admit that its clean narratives are provisional, that the universe may pass through distinct behavioral eras that don't scale smoothly into one another. Think of it like this. A child doesn't grow like an adult, scaled down. Growth spurts exist, hormonal cascades, abrupt reorganizations. After those transitions, growth slows, stabilizes, refines. The early universe may have gone through its growth spurt. We are living in its adulthood. And adulthood forgets how violent childhood was. This is where the human frame becomes unavoidable. We look back and assume our own past was inevitable, orderly, linear. Memory smooths trauma. History edits out chaos. The universe may do the same to us, presenting a calm present that hides an intense origin. Webb is ripping that edit open. It's showing us that the universe's early years were not gentle rehearsals. They were decisive moments that locked in outcomes we still live with. The distribution of galaxies, the abundance of elements, the placement of voids, even the background glow of radiation all carry the imprint of that early efficiency. This makes cosmology feel less like archaeology and more like forensic reconstruction. We're not just asking what happened, we're asking how fast it happened and why that speed mattered. Because speed is leverage. Fast processes outrun damping, they outrun smoothing, they outrun correction. Whatever forms quickly gets entrenched. And that has a chilling implication. If the early universe entrenched structure early, then late-time processes may have far less power to change the big picture than we assume. Dark energy may dominate expansion now, but it may be shaping an already decided landscape. Galaxies are already in filaments. Voids are already empty. The cosmic web is already set. Acceleration at the end may not rewrite the story. It may only stretch it thinner. And stretching is not the same as erasing. Now let's turn Webb's gaze inward again toward us. We exist inside one of those early advantage regions, a filament rich in galaxies, a neighborhood shaped by decisions made billions of years before Earth formed. Our cosmic address is not random, it's inherited. We are beneficiaries of early success. That doesn't make us central, it makes us contingent. Because had we formed in a region that lost the early race, one that stayed diffuse, star-poor, chemically barren, there would be no one here to notice. The universe didn't guarantee observers everywhere. It created conditions quickly and let consequence decide. That's not cruelty. It's physics without sentiment. Einstein once said the most incomprehensible thing about the universe is that it is comprehensible. Webb is complicating that quote. The universe is comprehensible, but only if we let go of the idea that it must be slow, fair, or incremental. Comprehension doesn't mean comfort. And here's the turning point. What Webb has done is shift cosmology from a story of gradual emergence to one of early commitment. The universe didn't test possibilities gently. It locked in winners early and let time elaborate on those choices. This doesn't end the story. It sharpens it. Because now, when we ask about dark matter, dark energy, inflation and gravity, we're not just asking what they are. We're asking what kind of universe they produce when time is scarce. That question is about to collide with the deepest unknown of all. Not what fills the universe, but what started its clock, and whether that start was smoother or sharper than Einstein ever imagined. Clocks are deceptive. We treat time as a neutral backdrop, a silent counter ticking evenly from beginning to end. But Einstein taught us something far more unsettling. Time is an outcome. It stretches, it slows, it thickens near mass and thins with motion. It is shaped by the universe as much as it shapes the universe. So when we say the early universe did too much too fast, we're smuggling in a dangerous assumption that time itself was behaving the way it does now. It may not have been. In the first moments after the Big Bang, the universe was not just dense, it was extreme in every dimension that matters. Energy density, curvature, expansion rate. In such conditions, time is not a smooth river, it's more like white water compressed, turbulent, violently effective. A short interval can accomplish an enormous amount. What looks like haste from our perspective may have felt like duration from the inside. This reframes the tension entirely. Webb's early galaxies may not be evidence that the universe broke its own speed limits. They may be evidence that the speed limit itself was different when the universe was young. Einstein's equations allow this. They don't enforce a universal tempo. They respond to conditions, and the early universe had conditions we will never recreate, conditions where time, as an operational resource, was abundant in consequence even if scarce in years. This is where cosmology and intuition part ways. We imagine the early universe as young and youth as unprepared, but youth, in physics, is intensity. High density means short distances. Short distances mean faster interactions. Faster interactions mean rapid outcomes. The universe wasn't inexperienced. It was concentrated. Now consider what Webb is really showing us when it detects these early structures. It's not just mass, it's not just light, it's coherence. Galaxies that rotate, cores that are dense, stellar populations that are layered. Coherence requires synchronization. It means processes didn't just happen, they happened together, across vast regions, with timing tight enough to lock in structure before expansion could tear it apart. That kind of synchronization is only possible in a universe where causal contact is efficient, where signals, influences, and gravitational effects can propagate quickly relative to expansion. Which brings us back to the very beginning. Inflation is often described as a smoothing process, ironing out wrinkles in space-time, but it also set the stage for causal disconnection regions that can never communicate again. If Webb is showing us unusually coordinated early structure, it may mean that coordination happened before those separations became permanent. In other words, the universe may have made its biggest decisions while everything could still talk to everything else. Once inflation ended, once expansion accelerated and horizons formed, those decisions became irreversible. This is not a technical footnote. It's the difference between improvisation and commitment. The early universe improvised under extreme conditions. The later universe inherited the results. And we are living inside that inheritance. There's a quiet emotional shift here that's easy to miss. We've long imagined ourselves as latecomers in a tired universe arriving after the drama, after the fireworks, after the important choices were made. Webb is flipping that perspective. The universe may have done its most decisive work early, but that work was not sterile, it was generative. It created environments rich enough, stable enough, and long-lived enough for stories like ours to unfold billions of years later. That's not indifference. That's resilience. Now let's bring Einstein back one last time, not as an icon, but as a guide. Einstein never finished cosmology. He opened it. He gave us the language space-time, curvature, relativity, but he knew the universe would always outrun the models built on that language. He expected surprises. He expected refinement. He expected humility. James Webb is delivering exactly that. Not a refutation, a reminder. The universe is not obligated to match our expectations of pacing, simplicity, or narrative elegance. It is obligated only to itself. And what it's showing us now is a universe that, when given the slightest opportunity, organized itself with startling speed and confidence. That realization doesn't close questions. It reframes them. We no longer ask, why did galaxies form so early? We ask, why wouldn't they, given the conditions? We no longer ask, was Einstein wrong? We ask, which regime were we blind to? And that shift is the real discovery, because it means the tension isn't between theory and observation. It's between our intuition and reality. The early universe didn't hesitate. It didn't wait to become interesting. It didn't defer complexity to some distant future. It seized the moment when everything was close, hot, and responsive, and it built. That moment is gone now. The universe is larger, colder, thinner, slower. But the structures born in that brief, furious youth still dominate everything we see, including us. And as Webb continues to stare back toward that origin, toward the last light before darkness, toward the threshold where the universe first learned how to build, we're approaching something that feels less like a discovery, and more like a recognition that the universe we inhabit was never timid. It was decisive from the start, and we're about to see just how deep that decisiveness runs. Decisiveness leaves fingerprints, not the kind you see at first glance, but the kind that only appear when you stop asking what exists and start asking why this pattern and not another. Webb is slowly turning cosmology into that kind of interrogation. Because once you accept that the universe committed early, you start noticing how stubborn its commitments are. Galaxies today still trace the same filaments laid down when the universe was young. Clusters still sit at the intersections of ancient flows. Voids are still empty because they never got a foothold when it mattered. The universe has been coasting on early decisions for billions of years. This is not evolution by constant revision. It's evolution by early lock-in. And that should make us uneasy, because lock-in means alternatives were possible and lost. Now feel the scale of that loss. There are regions of the universe so empty that star formation may never ignite there. Not because physics forbids it now, but because it missed its window then. Density never crossed the threshold. Gravity never got leverage. Those regions will remain dark forever, not by fate, but by timing. Timing is destiny in a universe that moves fast. This is where Webb's discoveries stop being about galaxies and start being about paths. The universe didn't explore every possibility equally. It explored some aggressively and abandoned others almost immediately. That's not randomness. That's selection. We usually reserve that word for biology, for life, for evolution. But selection doesn't require genes. It requires competition under constraint. The early universe had both in abundance. Dense regions competed for matter, hot regions resisted collapse, expansion rewarded speed. The winners became structure, the losers became void. And once that selection occurred, the game was effectively over. This is deeply uncomfortable for a culture raised on the idea of endless opportunity. The cosmos doesn't work that way. It offers opportunity briefly and then enforces consequence relentlessly. Einstein's equations are silent on fairness. They describe response, not justice. Webb is making that silence audible. Now turn the lens inward again. We exist because our region of the universe crossed critical thresholds early. Enough matter, enough cooling, enough time under the right conditions. If any of those variables had lagged even slightly, there would be no Milky Way, no Sun, no Earth. Our existence is not balanced on a knife edge of fine-tuning across all of physics. It's balanced on a race that was won early. That doesn't make us miraculous, and it makes us local. And locality matters in a universe that commits fast. This perspective also reframes the anxiety around Einstein's cosmology being shaken. What's being shaken isn't the math. It's the story we told ourselves about gradualism, about smoothness, about patience. Einstein didn't promise patience. He promised consistency. And consistency allows for violence, speed, and irreversible choice. Now notice something subtle. Despite all this early ferocity, the universe did not tear itself apart. It didn't collapse entirely into black holes. It didn't fragment into chaos. It threaded a narrow corridor fast enough to build structure, slow enough to preserve it. That balance is extraordinary. It suggests the universe was not just decisive, but stable under decisiveness. That's rare. Most systems that move fast overshoot and self-destruct. The universe didn't. It stabilized into hierarchy. That tells us something important about the underlying laws. They don't merely permit complexity, they regulate it. They allow speed, but they bound it. They let gravity win locally without letting it dominate everywhere. This is where Einstein's legacy reasserts itself, not as an obstacle, but as a guardian. General relativity doesn't let gravity act instantly or infinitely. It has structure. It has limits. Even black holes are contained. Even singularities are hidden behind horizons. The universe can be violent but not reckless. Webb is showing us a universe that used every bit of that allowance. Now consider the emotional reversal this forces. For decades, we've used cosmology to argue for insignificance, vast scales, long times, humanity as a footnote. That rhetoric leaned heavily on the idea of slowness of a universe so patient that our brief existence barely registers. But a fast-forming universe tells a different emotional story. It says the universe doesn't need eternity to become complex. It says intensity matters more than duration. It says brief windows can shape everything that follows. That makes our own window feel relevant. We are not important because we are large or long-lived. We are important because we exist at all in a universe that closes doors quickly. That doesn't center us. It contextualizes us. Now, Webb's role in this story is almost cruel in its simplicity. It doesn't editorialize. It doesn't speculate. It collects photons and lets them speak. The shock comes from how consistently those photons undermine our sense of pacing. Every early galaxy says the same thing in a different accent. We were ready before you expected. And as more data accumulates, cosmology is being forced to do something it hasn't had to do in a long time. Slow down its certainty. Not its curiosity, not its ambition, its certainty. This is healthy. This is how science breathes. Einstein's greatest contributions didn't close questions, they made better ones unavoidable. Webb is doing the same. The next unavoidable question is not about the past. It's about how much of the universe's behavior is front-loaded. If structure, hierarchy, and chemical richness all emerged early, what else did? And what else did we miss because we assumed it would take longer? We are now approaching the most destabilizing possibility of all, that the universe didn't just form its scaffolding early, but may have set the conditions for observers early too. Not us, but the possibility of beings who could eventually look back and ask these questions. And that possibility may be woven deeper into the universe's first moments than we ever dared to imagine. Possibility is not the same as destiny. But in a universe that moves fast, possibility doesn't linger. It either ignites or it vanishes. When Webb forces us to accept that chemistry, structure, and energy gradients emerged early, it quietly destabilizes one of our most comfortable assumptions that the universe spent most of its history uninhabitable, waiting patiently for complexity to crawl into existence. That picture now looks increasingly like a projection of our own developmental story. The universe may not have waited. The raw ingredients for complexity, carbon, oxygen, nitrogen, stable stars, long-lived galactic environments appear to have assembled shockingly fast. Not everywhere. not gently, but widely enough that the question shifts from when could complexity begin to how often did it get the chance. This is not a claim about life. It's a claim about readiness. Readiness matters more than outcome. A universe that becomes ready early creates a long runway. Billions of years where chemistry can explore, where planets can cool, where atmospheres can settle, where chance can iterate. Even if life is rare, time is generous. Even if intelligence is fragile, opportunity is repeated. That is a very different universe from the one we thought we lived in. And it emerges directly from the same early decisiveness Webb is revealing. Now feel the tension. A fast-forming universe is generous with opportunity, but ruthless with mistakes. Early radiation was intense. Supernovae were frequent. Black holes were active. Young galaxies were turbulent. Many nascent environments would have been sterilized as quickly as they formed. But that's not a contradiction. That's selection again. Most possibilities fail. Some survive. Those survivors inherit stability. We are not living in the early universe. We are living in what endured. This reframes humanity's relationship to cosmic history. We are not the fragile outcome of a gentle universe. We are the durable outcome of a violent one that stabilized. That's a heavier inheritance than we usually admit. Now we step back and look at the philosophical weight pressing on Einstein's legacy. Einstein's cosmology removed humanity from the center of the universe spatially and temporally. No special location, no special time. Webb isn't undoing that. It's doing something more unsettling. It's suggesting that while we are not central, we are timed. We exist in a universe where the early rush to structure created long-lived islands of complexity, and we happen to inhabit one of them while it's still viable. Not because the universe aimed for us, but because it didn't hesitate. That distinction matters. It preserves humility without erasing meaning. Now consider how this changes the emotional arc of cosmology. The old story leaned heavily on emptiness, vast voids, cold futures, a sense of inevitable dilution. Awe came from scale, but meaning drained away in the process. The emerging story is different. Awe comes from speed, from efficiency, from the fact that the universe wasted no time becoming capable of complexity. Meaning doesn't come from purpose, it comes from consequence. This is harder to romanticize but harder to dismiss. James Webb, unintentionally, is turning cosmology into a story about thresholds. Cross the threshold fast enough and structure locks in. Miss it, and the door closes forever. The universe may be full of closed doors. We just happen to be behind one that stayed open. Now feel how this loops back to Einstein one final time. Einstein gave us a universe where space-time reacts to content. Matter tells space how to curve, space tells matter how to move. It's a feedback system. Webb is revealing how intense that feedback was early on, and how decisive the outcomes were. This doesn't weaken relativity. It makes it feel alive. Relativity was never meant to be static. It describes a universe capable of evolution, instability, and transformation. We simply underestimated how eagerly it would use that capability. And now we're standing at a point where cosmology is quietly reorganizing itself around this realization. Not rewriting textbooks overnight, not discarding Einstein, but loosening the assumption that later always means more. Sometimes earlier means everything. As Webb continues to map the faintest light, to push closer to the first stars, to resolve the boundary between darkness and ignition, it is narrowing the window where our old intuitions can hide. The universe didn't ease into complexity. It leapt, and leaps leave shadows. We're about to step into one of those shadows now, the place where all of this speed, efficiency, and early commitment converge into a single, unavoidable question. If the universe was this good at building structure early, why did it ever slow down? Because whatever answered that question didn't just shape the past. It shaped the future we are now racing toward. Slowdown is never accidental. In systems this large, this energetic, this interconnected, nothing simply drifts into calm. Calm is achieved, paid for, enforced by exhaustion, by dilution, by the running out of gradients that once drove change. The universe slowed down because it spent itself. The early universe was dense, hot, and tightly coupled. Matter could find matter. Gravity could act quickly. Energy differences were steep. Every collapse released more energy to drive the next one. It was a feedback-rich environment, a perfect engine for rapid construction. But engines burned fuel. As expansion continued, distances grew, density dropped, radiation cooled. Interactions that once took moments stretched into eons. The same laws still applied, but their leverage weakened. Gravity still pulled, but across longer gaps. Cooling still happened, but more slowly. Collapse still occurred, but without the urgency of youth. The universe didn't choose patience. It aged into it. This is the missing emotional piece of Webb's revelation. The early universe wasn't exceptional because it broke the rules. It was exceptional because it had access to conditions we can never recover. A brief window where everything was close enough, hot enough, and responsive enough to build at maximum speed. Once that window closed, it closed forever. And that closure is written into the sky. Look around the cosmos today. Star formation rates are declining. Galaxies are running out of cold gas. Massive mergers are rarer. Black holes are quieter. The universe is still evolving, but the tempo has changed. This is not decay. It's aftermath. The universe is living off capital accumulated early. This reframes dark energy yet again. Dark energy didn't necessarily end the era of rapid structure. It may have simply arrived after it was no longer needed. Once galaxies were in place, once filaments were set, once chemical richness was widespread, expansion could accelerate without erasing complexity. The universe had already done the hard part. Now expansion stretches what exists instead of preventing its formation. This is subtle and devastating to our old intuitions. We assume dark energy robbed the universe of opportunity. But what if opportunity had already peaked? What if the universe's most creative phase ended not because of dark energy, but because success made restraint possible? In other words, the universe slowed down because it could afford to. That is not a weak ending. That is a confident one. Now bring humanity back into the center of the emotional frame, not as protagonists, but as witnesses. We are alive during the long plateau after an early burst of creativity, a time when stars are still forming, planets still exist, chemistry still works, but the universe is no longer inventing new large-scale structures. We are studying a completed architecture. That is an extraordinary privilege, because it means we can see the universe after its most decisive acts. But before its lights go out, we are not too early to understand. We are not too late to observe. We are in the observational sweet spot. And Webb is the instrument that makes that explicit by revealing how fast the universe built itself. Webb is also telling us something about limits. Not limits imposed by theory, but limits imposed by opportunity. There are phases of cosmic history where certain things are possible, and phases where they are not. Galaxy formation had its era. Black hole seeding had its era. Chemical enrichment had its era. Those eras overlapped briefly, violently, and productively. We live downstream of them. This forces a profound shift in how we think about cosmic significance. We are not significant because the universe is young and attentive. We are significant because the universe is old enough to remember what it did. Memory matters. The cosmic microwave background is memory. The distribution of galaxies is memory. The chemical composition of stars is memory. And Webb is turning memory into narrative. Einstein gave us the grammar of space-time. Webb is showing us the punctuation marks, the moments where the universe paused, accelerated, committed, and then let go. Now feel the emotional closing pressure. If the universe built fast, committed early, and then slowed deliberately into stability, then our future is not just about decline or expansion or heat death. It's about endurance within a finished framework. The universe is not actively becoming something else at large scales. It already became it. That means our role is not to witness creation, but to interpret it. To understand how a universe that had no obligation to produce complexity did so with startling efficiency, and then stepped back. This is where awe replaces anxiety. The universe is not rushing us toward oblivion. It is holding space long enough for reflection. Einstein once wrote that the eternal mystery of the world is its comprehensibility. Webb is revealing the other half of that truth. The mystery is not just that we can understand the universe, but that the universe built itself in a way that makes understanding possible at all. It didn't have to slow down when it did, but it did. And because of that, we are here not at the beginning, not at the end, but in the long, quiet middle, looking back at a moment of ferocious creation that still defines everything. There is only one step left now, one final zoom out, because once you see how fast the universe built itself and why it slowed, you're forced to confront the deepest emotional truth of all. The universe did not wait for us, but it made room for us anyway, and that room is closing slowly, quietly, without drama, which makes this moment our moment not small at all. Room is not infinite. It feels that way when we look up black sky, scattered light, distances so vast they numb meaning. But cosmology has taught us the opposite lesson again and again. The universe is generous, not boundless. It offers conditions, then withdraws them. It opens windows, then seals them, not out of malice, but because change has inertia. The room we inhabit exists because multiple cosmic clocks overlapped just long enough. Stars that live billions of years, galaxies that remain gravitationally bound, chemistry that stays stable, energy gradients that haven't flattened yet. Those overlaps are not permanent. They are a phase, and Webb's revelation sharpened that reality by showing us how brief and decisive earlier phases were. The early universe burned bright and fast, locking in structure. The later universe cooled and stretched, preserving it. The middle where we are is where complexity has time to notice itself. That middle will not last forever. This is not doom, it's proportion. A universe that rushed to build and then slowed to endure is not one racing toward annihilation. It's one that knows how to transition. What's ending now is not existence, but novelty at the largest scales. The universe has finished inventing galaxies. It is now letting them age. And aging at cosmic scale is quiet. This brings us to the final emotional inversion Webb forces upon Einstein's cosmology. We were taught to fear the future because of expansion, galaxies leaving, light fading, isolation growing. But isolation is only frightening if you imagine the universe still owes you something new. What if it doesn't? What if the universe already gave everything it was ever going to give early, efficiently, and at scale, and what remains is stewardship of the aftermath? That is not a tragic universe. That is a complete one. Einstein's equations never promised infinite novelty. They promised consistency, and consistency allows a universe to finish its work and then hold steady long enough for observers to appear. We are those observers. Not late, not early, precisely placed. Now let's return one last time to James Webb not as a machine but as an event. Webb didn't just extend our vision, it broke a psychological dam. It showed us that the universe's most important acts were not spread thinly across time. They were concentrated, focused, urgent. That realization changes how we feel about scale. Vastness no longer implies slowness. Age no longer implies patience. Distance no longer implies insignificance. The universe was decisive when it mattered. And because of that, our moment, though brief, matters too. We are living during the era when complexity can still look back and see how it came to be, when galaxies still shine, when stars still burn, when chemistry still organizes itself into minds capable of wonder. That is not guaranteed. It is temporary, and that temporariness is not a flaw. It is the point. Now slow the pacing, let the scale widen. Billions of years from now, stars will be rarer, galaxies more isolated, the cosmic web stretched thin. Observers, if any remain, will see a quieter sky. Stripped of the evidence Webb now reveals so vividly, they may never know how fast the universe once built itself. We do. We are alive at the one moment when the universe is old enough to have a story and young enough for that story to still be visible. Einstein gave us the language to describe the universe. Webb is showing us the tone it was written in. Not cautious, not hesitant, but bold. And boldness leaves echoes. The galaxies Webb sees are echoes. The black holes are echoes. The elements in our bodies are echoes. We are not standing outside cosmic history, analysing it from safety. We are inside it, composed of its fastest, most intense decisions. This is where the idea that Einstein was shaken finally resolves into something calmer and more powerful. Einstein was not shaken. We mistook elegance for restraint. We mistook age for gentleness. We mistook vastness for indifference. The universe is elegant, but it is not restrained. It is vast, but not indifferent. It is old, but it did its most important work young. And that brings us to the final closure, not of knowledge, but of feeling. The universe does not need us to validate it, but it allowed us to arrive during a window where validation is possible. We can see its early audacity. We can measure its consequences. We can tell its story. That is not an accident of time. That is the inheritance of a universe that built fast, stabilized wisely, and left just enough room for witnesses. One final message remains, not to explain, but to leave you with the only response that fits a universe like this. We end where we began, looking at something that should not exist. Not because it violates equations, but because it violates our instincts. A universe that builds galaxies before it feels old. A universe that lights black holes before it settles down. A universe that races towards structure, then slows just enough for reflection. That universe should feel reckless. Instead, it feels finished. James Webb didn't show us a mistake in Einstein's cosmology. It showed us its full temperament. Not just what space-time does, but how eagerly it does it when conditions align. Einstein gave us a universe that responds. Webb revealed how quickly it commits. And commitment is the key word. The universe committed early to structure, committed early to hierarchy, committed early to chemistry. And then, having done so, it stepped back. It let stars age. It let galaxies mature. It let space stretch without erasing what mattered. That is not indifference. That is restraint earned through success. We tend to think meaning must be inserted into the universe from the outside by observers, by stories, by belief. Webb is showing us something quieter and harder to ignore. Meaning can arise from timing, from the fact that the universe did not waste its brief window of maximum possibility. It acted. And because it acted decisively, we are here to notice. We are not the reason the universe exists, but we are evidence of how well it used its opening move. That realization doesn't make us large. It makes us included in a chain of consequence that began when everything was close, hot, and responsive, and has been coasting on that moment ever since. The atoms in your body were forged in stars that only existed because galaxies assembled early. Those galaxies only exist because gravity seized opportunity faster than expansion could erase it. You are not separate from that speed. You are made of it. Einstein once said that the most beautiful thing we can experience is the mysterious. Webb has shifted the mystery. It's no longer just that the universe exists. It's that it became capable of complexity so fast and then held that capability open long enough for witnesses to appear. That window is rare, that window is temporary, that window is now. And knowing that doesn't diminish us. It steadies us. Because in a universe that builds fast and commits early, the fact that we can pause, look back, and understand even part of what happened is extraordinary. Not because we are special, but because the universe made room for reflection after it finished creating. We are standing in that room, looking outward, and for the first time, truly feeling what kind of universe we're in. Not a slow one, not a timid one, but a bold universe that did its greatest work young and left the lights on long enough for us to see it.